Hello, everyone. First of all, I would like to thank you all, community members, audience, and my supervisor for taking your time and attending in my presentation. My PhD thesis is, the title of my PhD thesis is Myoelectric Control for Active Prostheses via Deep Neural Networks and Domain Adaptation. This work is done under supervision of Dr. Arash Mohammadi at Concordia University. First of all, I will define the problem, then I briefly present the literature review, then I will present my thesis work in three main sections. In each section, first I will talk about the challenges, then I will provide the contributions that I have done in each section, and these contributions will present in again in several subsections. So the main focus of this thesis is on SEMG-based hand gesture recognition. So when you want to do a movement, there are some neural activities initiated in your brain, and these neural activities are transferred to the muscles by electrical signals. After that, we can collect these control signals and give it to an algorithm. And because there exist some patterns in these control signals, we can detect and classify different hand gestures, and then give this control command to the prosthesis device. After all, we can close the loop and provide the feedback to the user. For collecting the data, we have two approaches. The first one is based on sparse multi-channel SEMG, where the number of electrodes are limited and it is sensitive to electrode shift or electrode location. One of the databases that here is public and very popular is NinaPro. On the other hand, we have high density SEMG signal where we have an array or a grid of electrodes. So the number of electrodes are too many, and we can capture both temporal and spatial motor unit action potentials in muscles. Two databases that here exist is CAP-MYO and CSL HD-EMG. The thing is that because of the nature of complexity here, of high density SEMG, they add latency to the processing pipeline. After collecting SEMG data, we have different control algorithms. So the control algorithms can be categorized in three main sections. The first one is conventional myoelectric control systems, which offer several benefits. For example, they are very straightforward to implementation, but the thing is that they have some disadvantages. For example, the limited number of degree of freedoms. The second category, which is specified by the orange color, is the main focus of this thesis. So it is about pattern recognition control system, which has two subcategories. The first one is machine learning, and the other one is deep neural network-based architecture. And the final category is about decomposing SEMG signal into motor unit action potentials. Then it is possible to extract some code from these MUAPs and then map it to the control commands. More specifically, here, for example, after collecting SEMG data from the muscles and after doing some pre-processing steps, we should segment those SEMG signal by a window. After windowing, we can use ML classifiers or deep neural network. If we are using ML classifiers, first we should extract the features by hand and then feed to those ML classifiers. But if we are using deep neural networks, we can both feed those handcrafted features or raw SEMG signal. And finally, we have control commands for the prosthesis device. So here I provide the public databases actually they are providing a common platform for the evaluation. In some of these databases, the objective is to increase the number of the users. In others, the objective is increasing the number of gestures or type of gestures. And some of these databases are investigating the effect of acquisition setup on the performance. And on others, they have actually collecting SEMG data in different sessions instead of focusing only on one session. And finally, I will complete this section by presenting this table, which is the state-of-the-art researches in pattern classification. So here, different inputs are used in different literature. For example, they can use raw SEMG or they can convert SEMG to the images and then use their algorithms, or they can use handcrafted features. Different methods or algorithms are presented. For example, CNNs, hybrid CNN, LSTM, or transfer learning approaches. And the focus can be different things. For example, improving accuracy or improving the robustness when there is electrode shift or electrode location, or for example, focusing on adaptivity for the new users or the new gestures. This will complete this section, the literature review and the introduction. Then I will move on the first section, which is accurate and efficient SCMG-based deep learning models for hand gesture recognition. First of all, I would like to define the challenges in this in the previous literature or research work. So the challenge number one is that the previous researchers only considered the spatial information. More specifically, they convert SEMG data to the image and then use CNN-based image classification. So they didn't consider the sequential nature of this information. Challenge number two is about improving the accuracy when data is collected based on sparse multi-channel SEMG signals. Challenge number three is when we use LSTM or RNNs for sequence modeling, and they have some problems that I will talk more about it in the following slides. Challenge number four is about the number of parameters in DNN models. Sometimes DNN models have a lot of parameters, and it is challenging to embed them into prosthesis controllers. Challenge number five is about when some architecture needs input sequence permutation. And finally, challenge number six is about when the architecture is dependent on the window size. It means when we change the window size, the architecture should be reconfigured. So here for this section, we propose three solutions. The first one is HRM architecture that address challenge number 1 and 2. The second one is TCN architecture, which addresses challenging 1 and 3. And finally, we have exception time architecture, which addresses challenge number 4, 5, and 6. More specifically, HRM, which is a hybrid recognition model, is developed to first improve the accuracy and second extract temporal and spatial features. Then we propose TCN architecture. Actually, the thing is that all of the time when we have sequence modeling, the first thing that comes to mind is using recurrent-based architectures. But here we show that if we use convolutions in a proper way, we can improve the accuracy, improve the performance. So we developed TCN architecture here. After that, we propose exception time architecture, and the motivation is that only focusing on the improving accuracy is not enough. So it is better to reduce the number of parameters as well. So for the exception time architecture, we have two objectives: improving accuracy and reducing the number of parameters. So I will start with the first architecture in this section, which is hybrid recognition model. So here, as you can observe, we have a hybrid recognition model, so which is consists of two parallel paths. The first one is CNN block, and the second one is LSTM block. So the contributions that we have done this here as the first step is that we are extracting spatial and temporal features here. More specifically, in the previous works, they converted the CMG signal into image. So the way that they are converting those signals to the image can affect on the accuracy. So here we use one CNN block in the way that it can extract these features, and it is not necessary to convert this CMG signal into images. After all, the results from the CNN block and LSTM block are flattened and concatenated and then feed to the MLP layer. So as I mentioned, we wanna use convolution in a way that we can improve the accuracy and performance for SCMG signals. So it is proven that it is not the case that RNNs always outperform CNNs, and if we design CNNs, we can outperform the result. So here, the contribution that here we have done in this architecture is dilated causal convolution. And the reason is that if we only use the problem with standard convolution is that they have a limited kernel, and they didn't consider the long-range dependencies. So for considering that history and access a large history field, we can use dilation. So as you can see, we can stack more layers and increase the dilation factor. For example, it starts from 1, 2, 4, 8. So we can increase the receptive field. And here, another thing that we consider here is that we don't need the input sequence permutation. So we use one-by-one convolutions, and we increase the dimension and concatenate them and then feed to main block. The first block here is identity block, and the second one is convolutional block. So in both of those blocks, we are using skip connections. The reason is that when we have a deep neural network, it is not the case that the result will be improved by, for example, stacking more layers because of vanishing gradients. So we added skipping connections here for both identity block and convolutional block. And if the dimension of input and output mismatch, we are using one-by-one convolution. Here is the formulation of dilated causal convolution. So for example, if we have the input sequence X, we can use a filter F with kernel size of K and with dilation factor of D. In each layer, we increase that dilation factor. Before presenting the result, I would like first to talk about the database. So we are here using DB2. The DB2 is collected at a frequency of 2 kilohertz. It is collected from 40 users, and each user is performing 50 gestures. And these gestures are presented in 3 exercises, exercise B, C, and D. And here we are focusing on exercise B, which has 17 gestures. And in this data set, each gesture is repeated 6 times. Each time is lasted for 5 seconds. Here is an illustration of SEMG data. So the green color illustrates SEMG signals, and we have a blue dashed signal that it is related to the original labeling. It means that when the volunteer observed this blue signal, he or she should perform the gestures. But the thing is that sometimes there is some delay in his reaction. So we should refine those labeling, and the refined labels which refer to the posterior label is illustrated with the red colors. For both of the prior and posterior data, here we report the accuracy for both our method, which is HRM and TCN, and we compare our result with reference number 48. In reference number 48, actually, they are using convolutional blocks or CNN models, and they use different configuration of those CNN models. For example, in CB1, B2, they are using 2 parallel paths. Each path is a convolutional, a CNN block, block 1 and block 1. Block 1 and block 2. Or for example, C2B1 is when they are using block 1 2 times in parallel, and so on. So we can see that there is an improvement in the accuracy for both for the posterior data, and unfortunately, reference number 48 didn't report the accuracy for the prior data. Here is the confusion metrics for the TCN. Actually, here we have 17 movements, and based on that confusion metrics, we can calculate precision, recall, or accuracy very easily. And the other information that we can get from these confusion metrics is see that, for example, some gestures, the classification for some gestures is not good enough, and this is because they are more complicated, or some of these gestures are very similar to each other. And here we have the confusion metrics for HRM. So these confusion metrics for HRM is better than TCM, and this can be observed in the table as well. So I will move on the next subsection, which is exception time architecture. So the motivation here is to reduce the number of parameters and is to have an architecture that is independent on the window size. So if I change the window size, I don't want to change the architecture as well. So our contribution here is first using this wise separable convolution. instead of a standard convolution. So in the depth-wise separable convolution, we have a depth-wise convolution. It means that we convolve each channel independently from the others, and so the depth is fixed. And then we apply a point-wise convolution. It means that we can change the dimension or change the depth as well. More importantly, here, instead of restricting ourselves to only pick one kernel, we are using different kernels. But the problem here is that when you are using different kernels, we can increase the number of parameters. So to address this challenge, we are using a one-by-one convolution before that. And another thing is that we wanted to have an architecture that is independent on the window size. So we are using adaptive average pooling instead of fully connected layer. When we are using adaptive average pooling, it means that if you change the window size, you can, it is not necessary to change or reconfigure the architecture. And another important point here is that adaptive average pooling doesn't have any parameter. So it means that this is another step to reduce the number of parameters. The data set that here we are using is DB1 that is collected from 27 gestures. And again, each gesture is performing 27 users, and each user is performing 72 gestures. So here we have two tables. In first table, actually, we have two experiments. The first experiment is to verify that this architecture can reduce the number of parameters. So we have two type of version of model. The first one, exception time, and the second one is exception time version 2. So in exception time version 2, we are using a standard convolution, and you can see that we reduce the number of parameters while improving the accuracy. Another experiment that here we are using is to validate our claim that by using Myoelectric normalization, we can improve the accuracy. Actually, here we propose this type of technique for normalization. And for example, if you look at the window size 50 milliseconds, you can see that the result for min-max is about 71%, but for Myoelectric is about 81%. And finally, the final table is to claim or validate that this architecture is dependent on the window size. So instead of training the model only with a specific window size, we train the model with a combination of different window size, and then we test for a specific user and report the result. I will conclude this section by comparing our work with previous architectures. So the first thing here is that in a lot of works, they didn't report the model parameters, but for example, some of these work report the model parameters, and we can see that we improve the accuracy and we reduce the number of parameters. Here is the summary of the work that I have done in this section. We propose three sections. We propose three architectures. The first one is hybrid recognition model, that it was based on the parallel path, and it has several advantages. For example, it can capture both spatial and temporal features, and it can improve the accuracy. Then we propose the TCN architecture, which is based on dilated causal convolutions. In this architecture, in compared to HRM, has less memory requirement, and more importantly, it allows parallelization during the training, because when the model is based on a recurrent base, in each time step, we should wait for the result from predecessors. But in the TCN, we have parallelization during the training, and it can improve the performance. Finally, we have exception time architecture. The motivation is to reduce the number of parameters and to improve the accuracy, and that is an architecture that is independent on the window size. In the second section, we have attention-based model for hand gesture recognition. So far, I was focusing on architectures that they are based on recurrent-based solutions or using convolutions in a proper way. But here we can propose two architectures. The first one is TCHER, and the second one is TMGNet. So actually, TCHER, which is temporal convolutional based hand gesture recognition, is based on attention and temporal convolutions. And the motivation here is use attention besides the temporal convolutions. And we can see that by doing this step, again, we can have improved the accuracy and reduce the number of parameters. And after that, we propose TENG-net, which is only based on the attentions based on the transformers. And we wanted to investigate the effect of using transformers for the SEMG signal. So I will start with the first architecture, which is TCHGR architecture. After segmenting, so we have segment X. So after we collect SEMG data, we should segment those signals by a window. So after segmenting, we are patching this segment, and we have two main building blocks here. The first one is self-attention, and the second one is temporal convolutional block. So more specifically, we have a data set that is a set of segments, and each segment has a label. And after that, each segment is divided into n non-overlapping patches. The reason is that we wanted to reduce the computational burden. And then we are using temporal convolutional block. Again, we are using dilation convolution because we wanted to access a large receptive field. And the number of these blocks is in a logarithmic scale, and it is a function of number of non-overlapping patches. Finally, we have self-attention module. Actually, in the self-attention module, we want to measure the similarity of each query with all of the keys, and then assign a weight to the values, and the output is the weighted sum of those values. So here we reported the result in two tables. In the first table, we can see the description of the TCHGR architecture, and we want to, for example, investigate the model dimension B. So when we increase the model dimension B, for example, from 12 to 16, we can see that we can improve the accuracy, but the trade-off is increasing the number of parameters. Another experiment here is investing the effect of number of patches. For example, when we increase the number of patches from 10 to 16 or 10 to 15, again, we can improve the accuracy, but we have a more complex network. And the thing is that we report the result with different window size. So when we have a larger window size, it means that we provide more information to the network. So it is obvious that we can get better accuracy. But the thing is that when we are using a larger window size, it means that we are increasing the number of parameters. So here we have a statistical analysis between different models. For example, we compare model number 1 with model number 2, 3, and 4. The reason is that model number 1 has at least number of parameters. So we can see, for example, model number 1 and 3, they are not statistically significant. So if here I want to use, if I want to pick a model, I will pick model number 1 because it has at least number of parameters in comparison to model number 3. But if I want to pick, for example, model number 1 and 4, that depends on the level of accuracy that we need. If we want to have a model with higher accuracy, it is obvious that we should select model number 4. But if we are focusing on decreasing the number of parameters, we should select model number 1. And finally here, we compare our result with reference number 63 in the first table. So in the reference number 63, they are using LSTM and dilation LSTM. So we compare our result with them, and we can see that we reduce the number of parameters, for example, from 1 million to 50,000. And we have that accuracy. For example, our accuracy is about 81%, and their accuracy is about 82%. So we reach that accuracy with reduced number of parameters. And finally, we have the second table. In this table, we report the accuracy for each gesture. And for example, for gesture 11 and 12 here, we can see that the model distinguished these gestures with lower accuracy. And the reason is that they are similar gestures. They are, for example, wrist supination and pronation. So the same muscles are used here. So it is harder for network to distinguish them. So selecting the type of these gestures and selecting those gestures can affect the accuracy and the performance of the model. Finally, in this section, we will have TNG-net architecture, which is based on the transformers. So we have two blocks here, transformer encoder, which consists of multi-head self-attention and multi-layer perceptron. More specifically, after having the data set and each segment, we should divide that segment into some patches and then embed them into the patches into a vector and then convert it to a new vector by using matrix E, which is shared among all of the patches. And we are using here positional embedding because the problem with attention is that they didn't consider the order or the sequence. So we wanna encode the positional information as well. Finally, we have a sequence of this vector, which is Z0, and it is the input for the transformer encoder. The transformer encoder consists of L-identical layers. Each layers consists of multi-head self-attention and multi-layer perceptron. The result of final layer is used for the classification. So here we have the table. So we can see that by increasing the model dimension, the performance will be improved. For example, if we increase the model dimension from 32 to 64, the accuracy will be improved. But again, we are increasing the number of parameters. Moreover, we are investigating the increasing the number of layer from 1 to 2. So if we increase the layer from 1 to 2, we can see there is an improvement. But if we increase the number of layers to 3, we can see that there is no improvement in the accuracy compared to the case that we have only 2 layers. Here again, we report the result for 2 window size. The first one is 200 milliseconds and the second one is 300 milliseconds. So by increasing the window size, it means that providing more information. So we are improving the accuracy. Here we compare our method, which is TNG-net, with the previous works. One of these work is our previous architecture, which was based on attention and temporal convolution. And the other work is based on the LSTM, dilation LSTM, and one of them is STM. So here we can see that we achieved a good accuracy with at least number of parameters. And here again, we provide the statistical analysis in the first figure. So one of them is related to window size 200 milliseconds, and another one is related to the window size of 300 milliseconds. So in both of these sub-figures, we can see that there is no statistical difference between model ID1 and model ID3. Actually, model ID3 is related to the case when we increase the layers. So it means that it is better to pick the model number 1 because it has lower number of parameters. And finally, we visualize the positional embedding similarities for both model 1 and model 4. So here we have 50 patches. So the indexes start from 0 to 50. And we can see that the main diagonal is yellow. So it means that the neighbors are similar and the network is able to extract those positional information. Finally, I will conclude this section by the summary. So here in this section, we propose the 2 architecture. The first one is TCHER, which is based on self-attention and temporal convolution. By using temporal convolution besides attention, we can achieve a high accuracy and it allows parallelization during the training time. We can access a large receptive field, and we can pinpoint a specific information into the sequence by using attention. After that, we propose transformer-based architecture, which is based on the transformers, and it is less complex when compared to TCHER, and it has a lower number of parameters. Finally, we have in this section adaptive-based models for HER. The thing is that so far we will focusing on improving the accuracy or reducing the number of parameters. But the thing is that the train and test data comes from the same distribution, comes from the same user. However, the idea here is, what about if we want to adapt the model to new users, adapt the model to the new gestures? So we propose here FSHER, which is based on a fusion learning formulation. More specifically, another motivation here is that when we are using deep neural network models, it means that we should provide a lot of information or a lot of data. But the performance drops when there is no enough input or enough information. So we want to have an adaptive-based model that relies on minimal training data while providing high accuracy. So here you can is generalization across task rather data point. So here we are constructing tasks, and each task consists of data support two sets. The first one is support, and the second one is query. And here we have meta set, for example, meta train, meta test, and meta validation. And as you can see, each task consists of n-way cashot. For example, the task number 1 consists of 5 classes, because it is the n is equal to 5 and k here is equal to 1. It means that from each class, we select only one observation. And in the support set, we have the label of those observations, but in the query set, we don't have the label. So the network should predict the missing label for the query set based on the knowledge that it has obtained in the support set. And if you can, here we have meta test that we have another distribution. This distribution is similar to the distribution in the meta train, but it is not the same. So we can, for example, we have new gestures or new users during the testing time. More specifically, in the support set, when we have an observation, we should concatenate that observation with the label and construct the support set. But when we have query set, we have the observation without the label. And the network should predict the missing label of this observation in the query set. So here is the architecture. So after constructing those tasks, we should fit to the model. So the model consists of attention modules and temporal convolutional networks. So each temporal convolutional network consists of several temporal blocks, and each temporal block consists of dilated causal convolutions followed by ReLU, and the result of output of the ReLU and input is concatenated together. So here we have the experiment and the result. First of all, here we want the accuracy when we have the new repetitions. It means that, for example, if for each gesture we have 6 repetitions, 4 repetition is for the training and validation, and 2 repetition is considered for the testing. So we can see that when we increase the number of shots, we can increase the accuracy. Because from each class, we are observing more examples or more examples. And we compare our approach, which is based on the meta-learning, with other techniques, such as DNA-based model and classical method. And we can see that, for example, for 5-way 10-shot, we improve the accuracy for the new repetitions. And here we report the average time for a task, both in the time. So we can see that the test time is testing time is a small values. So it means that they can be used for real-time application, and based on the number of shot and the accuracy that we need in the real applications, we can, for example, select the shot, for example, 1, 5, or 10, because when we increase the shot, we have higher accuracy. But the thing is that a higher shot means that it takes more time. So it is a trading between testing time and the number of shot and the number of accuracy. And here we have the experiment when we have new user. It means that, for example, consider that we train with 27 users, and then we want to have a new user during the testing. For example, here we have 27 users in the training, 5 users in the validation, and 8 users in the test time. So there is no, the network is observing completely user during the test time. So here we can see by increasing the number of way, the accuracy will be decreased, because when we are increasing the number of way, it means that the more number of classes. But when we are increasing the number of shots, the accuracy will be improved. And in the second table, we have two experiments, experiment 2A and experiment 2B. Experiment 2A is related to the case that the tasks are constructed based on the specific user. It means that the number of classes and the number of shots are coming from the specific user. So it is harder for the network to distinguish the different classes. But experiment 2B is related to the case that the task is constructed based on several users. So the accuracy is better, but experiment 2A is more realistic than experiment 2B, because we want to network to distinguish between different classes, not distinguish the gestures that comes from different people. And here we have the statistical analysis between different users for 1 shot and 5 shots. So it observed that when we increase the number of shots, they are statistically different. Finally, here it is related to the case when we have new gestures in during the test, not the training and not the validation. So here, for example, we have 34 gestures in the training, 6 gestures in the validation, and 9 new gestures in the testing. So we use different embedding modules, and we report the result for different way and different shots. So when we improve the number of shots, it means that improve the accuracy. And finally, here we compare our result with the previous architectures. So here we are using Nina Pro DB5. In the Nina Pro DB5, we have 10 users. So when in the previous literatures, when they want to, for example, detect the classification for a new user, they use transfer learning. It means that they pre-train the models with 9 users and then fine-tune it for the for the 9 users, and then fine-tune it with a new user. So when we compare our results with the DNN methods and classical methods, we can see that we improve the accuracy in, for example, 2.6 seconds. But for that transfer learning approaches, they need 10 seconds for the calibration and fine-tuning to approximately achieve that accuracy. Finally, here we have conclusion. We presented our work in 3 sections. The first one was accurate and efficient SCMG-based deep learning method. So on that section, we proposed 3 architecture. The first one was HRM, which is a hybrid recognition model. The second one was TCN, which was a temporal convolutional network. And finally, we had exception time. After that, we focused on attention-based models. So we proposed 2 architecture. The first one was TCHR, and the second one was TEMGNet. And after that, we focused on the adaptive-based models. So we proposed an architecture which is trained based on minimal training data and can be adapted to new users or the new gestures. The future direction is to investigate other factors that can affect on the performance. For example, the electrode shift, electrode location, the position of the Rs, and when the data is collected in different sessions. Moreover, we can investigate the level of amplification on the performance. And it is very good to enrichment the CMG signals with other modalities. Finally, if we can provide some feedback to the user, he or she can interact with the environment much more better. And here you can see the publications that is achieved throughout this PhD thesis. And thank you for your attention.